Welcome to Topic 4 of the MOOC, Designing the Energy Transition, Simulation Models Towards a Sustainable Society. Topic 4 is entitled Energy Infrastructures and Land Use in MEDEAS, and this session is dedicated to land use. This session will start by presenting the land as a general issue in the context of the energy transition. Second, the basis of land use modeling in MEDEAS will be illustrated. After that, the land requirements, according to different scenarios proposed, will be presented. And finally, some examples of the competition issues potentially generated by land energy use will be proposed. Land is a problem in energy transition because, as shown in the previous session, energy production in general and renewable energy production in particular requires materials, more energy, but also land to be feasible. Human occupation of land has increased with population growth. In this graph, we can see that according to United Nations statistics, human population has more than doubled in the last 60 years, and future projections predict a growing pattern. Furthermore, land is not empty, but being increasingly occupied by human activities like agriculture, livestock, or urban expansion, as illustrated in the graph below. The consequence of this growing and occupation is that land is becoming a relevant constraint for future human activities. Unfortunately, as shown in the figure, renewable energy sources require more land to produce the same quantity of energy than fossil fuels. This is particularly relevant in the case of biomass, which is the most land-intensive source of energy, around 2,000 times more land than fossil fuels per unit of energy generated. Then, conscious management of land uses is one of the key points to guarantee a feasible energy transition to renewables. Taking account of this phenomenon, the MEDEAS model makes a first approach to the land requirement of energy transition. MEDEAS considers transformation of current marginal or crop lands to biofuels, and land needed for electrical renewable sources. First, using the model installed capacities and the power densities associated with the different renewable sources to calculate land requirements for electricity from renewables. Power density can be customized by the user according to specific coefficients in the parameters sheet of the inputs file. And second, the same logic is applied to calculate marginal and cropland area required to meet the defined potential of the biofuel production. As in the previous case, the different variables can be customized by the user in the parameters sheet of the input file. This is a first approach to have big numbers in order to consider transition feasibility in land terms. Following two examples of land requirements of energy transition pathways. This is a graph illustrating results for two examples. An example using the business as usual scenario corresponding to the IPCC SSP2 baseline scenarios, just expanding current patterns, and another one using a green growth scenario corresponding to the IPCC SSP2 OLT scenario, showing a higher effort to develop a renewable energy mix for electricity production starting in 2020. All of them consider a constant urban land. As shown, in the case of the business as usual scenario, the transition to renewables would require more than 275 million hectares of land devoted to energy purposes in 2050. If an acceleration of the introduction of renewables is expected, a green growth scenario, then land required would go beyond 300 million hectares. With these figures, and since the land potentially transformable is not abundant, many issues in the competition for land have appeared or will appear in the future. Some of the most relevant issues associated to this competition will probably be, first, the competition between energy production in solar farms occupying fertile land and solar on rooftops occupying urban land. Second, in a world with famines, the competition between land for food in the croplands and pastures and land for fuels, biofuels. And finally, the third, the competition between land for fuels and biodiversity conservation. To summarize with some conclusions about the topic, we can highlight that the transition to a system based on renewable energy needs the construction of infrastructures that require time, materials, energy, and land. Transport in MEDEAS is modeled through bottom-up policies considering the change to alternative vehicles. Mineral extraction is also considered in MEDEAS. Some critical minerals for renewable energies might reach exhaustion. Static and dynamic ROI are calculated in MEDEAS. Fast introduction of renewable energies has the potential to lower the ROI of the whole society. Also, a first approach to the land use requirements of energy transition has been carried out in MEDEAS. We have considered the project patterns of marginal and crop lands used for biomass and also the land requirements due to the increase in renewables for electricity according to their power density. And that's all about topic 4. In the next topic, we will have a look to the climate change modeling in MEDEAS. Thank you for your attention.